Hello, everyone. Welcome to the latest in our webinar series. Today, we're going to talk about the brand new Array-NRC classification, which was defined in the latest version of ASTM C423, which was just released at the time of this recording about a week or two ago. My name is Eric Wolfram. I'm the laboratory manager of Riverbank Acoustical Laboratories. And I also, at the time of this recording in 2023, I am the current chair of the ASTM E33 committee, which oversees the building and environmental acoustic standards developed and published by ASTM. And I also was the leader of the task group that developed this classification. So we've been working on it for maybe 5 to 7 years, and it's been a long process, and we're just super excited that it has been released. And today I'm going to go over a little bit of the basics of what it is, what the results mean, and then how it's calculated. As we go, please put questions in the chat. If you have any questions as we go, enter them in the chat. And then at the end, Becca will read them and I'll answer those questions at that time. Or at the very last slide will be an email address, and you could feel free to email me directly at that email address at any time. So. All right, with that, let's get started. So just to start, let's talk a little bit about the units of measurement. The ASTM International Standards are published and defined in the International System of Units, the SI. So you know these as meters, kilometers, and the unit of sound absorption meters squared. This is also sometimes called a metric Sabin, but for whatever reason, ASTM E33 committee has used the term sound absorption meters squared to define the unit of sound absorption. Those of us in the United States are very familiar with the inch-pound system of units, and the architecture industry still very heavily relies on inch-pound system, so feet, inches, and the unit of sound absorption in that system of units is the Sabin. So when we kind of go over the concepts here, I'm going to use the term Sabin because I think it's a little, it'll be less confusing for you, especially when we start talking about Sabins per square foot, which is a lot less confusing than meter squared per meter squared. But just know that once we get into the ASTM standards and how they're defined, we're going to switch over into the SI system of units. And just a note that sound absorption area meter squared per object often looks like sound absorption coefficients, but they're not the same thing. So, and we'll talk about that in a little bit. So for some of you, this will be very basic review, but some of the acoustical consultants and acousticians that are on the call will have covered this in the first year of their acoustics education. However, a lot of the people on the call are not acoustics experts. Some of them are, from, for example, the lighting industry or other architectural products industries. So we'll just kind of cover a little bit of the basics so people understand what these concepts mean. So with the NRC classification and with ASTM C423, the fundamental phenomenon that we're concerned with is reverberation time. So this is measured in terms of time. So it's the time it takes a sound field to decay 60 decibels after the source has been interrupted. So if you are running a steady state signal and you cut that signal, it's from that time the input source stops till you can't hear it anymore, basically, is the reverberation time. Similarly, if you create an impulsive sound and clap, you can hear then directly, how long that impulse takes to decay. Now, both of those aren't exactly how instrumentation measures reverberation time, but they give you a sense for, what we're talking about when we mean reverberation time. It's the length of time of that continuous echo. And so a sound source in a room produces sound waves which propagate through the air. When they reach a solid, hard surface, that those waves reflect back in a predictable way. In this drawing or rendering to the right, you see kind of an illustration of maybe an impression of a single kind of sound wave reflecting. This is maybe an oversimplification. In fact, this source is creating sound that's propagating in more than just this straight line. It's going in all directions all the way around it to varying degrees. And then as the sound is propagating, it's continuously dispersing. So what you have with reverberation is not just a single reflection, but a compounding of countless reflections off of every surface within the room, which are arriving back at the listener at different periods over time. So this reverberation, most of the time, in most cases, is detrimental to the function of a space. So, maybe, for example, an auditorium where a person is speaking over a public address system, reverberation can interfere with the ability of the audience to understand what's being said or understand the content of speech. There are some examples of spaces where reverberation is helpful to varying degrees. So, for example, a concert hall that specializes in classical music or choral music, they want some reverberation. They want some response for the room because it would make the instrument sound more full. It will make the music sound like it's coming from everywhere, and it'll just sound fuller and warmer and bigger. On the extreme end of the spectrum, and the types of content that want reverberation would be like Gregorian chant or pipe organists. Some pipe organists cannot get reverberation times that are too long, but for speech, for something like amplified rhythmic music, reverberation is a problem, and it's a type of noise. So Wallace Sabin, who is seen as the founding father of architectural acoustics, created an equation over 100 years ago to quantify or predict reverberation times in a room. So he could predict with this simple equation the reverberation of time of a room based on its air volume, its cubic air volume, and the total units of sound absorption present in the room, the total Sabins. So as the quantity of Sabins increases, the reverberation time decreases. So you could measure an existing room, you know its reverb time, and if you had a target for what your desired reverb time would be, you would know, you could solve for what's the increase in Sabins that we need to get to from our current reverb time to our target reverb time for a specific room. This was the start of acoustical consulting. This was the start of acoustical materials, and that's where it all began. So now, in truth, the definition of a Sabin is this equation. It's this item here in the equation. In trying to explain what this means, what is a Sabin, we've used different metaphors. The acoustics industry has used different metaphors over time to try to communicate what we mean. And I think one of the originals was that a Sabin is like 1 square foot of open window, or 1 square foot of perfectly reflecting surface, or perfectly absorbing surface. So in this photo here to the right, we have kind of an illustration of a wall, and some of the surfaces of the wall are reflective to light, and then some parts of the wall are not reflective to light. They're basically like a hole where the light goes in and doesn't come back. So you could think of a Sabin as being like 1 square foot of this open window where none of the sound is reflected back. So a hard, solid surface will reflect sound back, and a sound absorptive surface will consume it so that it doesn't reflect back. Again, this is sort of a metaphor. It's not the actual definition of a Sabin, but it's a really good kind of entry understanding of what a Sabin is. So the ASTM C423 test method is the way we as a laboratory try to measure the Sabins that a material or product or system will add to a space. So basically the total absorption added by an object. In this photo here is an example of an office screen. So basically in this test, we have a variation of the Wallace-Sabin equation, which is solving for the sound absorption, using the inputs of the volume of the reverberation room in cubic meters, and the speed of sound in the room, and the decay rate, the decibels per second rate of decay of sound measured in the chamber. So we will make this measurement in the empty reverberation room, and then add or install the product under test, and then make a second test with the absorption after the specimen has been installed. So that the additional sound absorption is the difference between those two. So it's A2 minus A1. So, and that is the total absorption provided by whatever it is that has been tested. Now, if the what is it that was tested is a flat two-dimensional surface treatment, then we can go one step further and we can calculate the Sabins per square foot of material. So remember, approximately 1 Sabin is 1 square foot of sound absorbing material, of perfect sound absorption. And let's say we had 72 Sabins of material at a certain frequency band that was measured in this instance, and we had 72 square feet of material, or truly 72 square feet of test surface covered by the installation of material, then we would have something called a sound absorption coefficient of 1.0. Now, this term that is very commonly used in the science of acoustics, it's a little bit of a misnomer, and some people that come in from other areas of physics are sort of surprised that sound absorption coefficients can exceed 1.0. They can exceed 1.0, and they often do for highly sound absorbing materials. This should be impossible if sound absorption coefficients were a true energy absorption coefficient, because by the laws of thermodynamics, that would mean that more energy has been absorbed than was even received by the material. But the truth is that in architectural acoustics, this term sound absorption coefficient means something a little bit different. We use this term to describe the Sabins per unit area of material, the sound absorption per unit area, the Sabins per square foot, or the sound absorption per unit area. And this is why you can have sound absorption coefficients that exceed 1. With these flat materials, we take that total added sound absorption, so the area added by, or area of absorption added by the material, and divide it by the area covered by the test specimen, and that's sound absorption coefficient. So noise reduction coefficient, NRC, is a single number rating, a classification that has been defined historically by ASTM. It's a way to communicate a single number rating or an average sound absorption coefficient for a type of material. Its definition is the average of the 4 1/3 octave bands at 250 hertz, 500 hertz, 1000 hertz, and 2000 hertz, rounded to the nearest 0.05. Now, there are some issues and concerns with this as it's defined. It takes kind of it tries to create a rating based on just these 4 frequency bands This method of rounding is sort of an older way of looking at things, where what the intent was that you don't want to overstate your precision in the test results. So they would round to the nearest 0.05, the thought being so that you don't have like a NRC 0.75 material and then an NRC 0.76, but the uncertainty of the test is about that, and they're actually the same performance, but just happen to have slightly different results. So that was the thinking by rounding it to 0.05. The problem with that is that rounding can actually introduce error. It can expand that difference. So you could have materials that test, I mean, it can happen where you have materials that test a 0.001 or 1,000th sound absorption coefficient difference. But because they fall right on both sides of that rounding, it'll expand that difference to 0.05. So you get 0.65 rather than 0.70. So there is a newer classification called the sound absorption average, which was introduced by ASTM a number of years ago. The intent was that should replace NRC. It solves all the problems of NRC, including the confusing name. And all Riverbank reports currently include both of these classifications. It's something we talk about at ASTM, that the architecture industry has famously ignored SAA and continues to specify NRC. But those are how those two are defined. So in the past 5 years or more, we've seen a kind of growing trend of spaced object arrays in architectural spaces, and many different types of felt baffles and fixtures that might be considered as an alternative to continuous sound absorbing treatments. The problem here is that there is no classification for these currently. Remember when we said that essentially NRC, which is the classification that the architecture industry relies on for speccing materials, NRC's true definition is sound absorption per square foot. And the area of these objects is not as easily defined as you might think. So we at ASTM have basically argued for years about what would be the way to calculate sound absorption per square foot for these types of objects. We have, if you go to our website under Education tab, we have a whole webinar on that struggle and on the different possible ways one could have arrived at sound absorption coefficients for baffles. Fortunately, ASTM has settled this subject once and for all, hopefully. So on May 10th, 2023, ASTM International published ASTM C423-23, which just means the 2023 version of C423, which includes a non-mandatory Appendix X2. So in this appendix, we state that the sound absorption per object, i.e. the Sabins per object, remain the preferred test result for suspended object arrays. So for acoustic baffles, we will still be reporting the total absorption and the absorption per object, which is maybe technically the most correct way to present the added sound absorption for a baffle. And that will really remain for types of objects that are greatly spaced apart. That will still remain likely the only good option for presenting results. However, we're introducing sound absorption per meter squared, which may be calculated using the extended continuous surface area attributable to the array of objects. And this extended continuous surface area shall be determined according to the procedures defined in ASTM C423 Appendix X2, which we'll go over now. So there's currently two types of arrays where this will apply. Over time, the intent is that we'll add more. And then as these are added, then the sound absorption for S-array and sound absorption or Array-NRC can be calculated for those later added configurations. Right now we've started with the two most common or the two most obvious configurations. So for example, if the set of objects consists of a rectangular array of equal sized objects with equal space between each object in a row and equal space between rows, so think of like a rectangular array where you have, let's say, 2 rows or 4 rows of 2 objects, for example, then the surface area of the array is the area of continuous surface attributed to the specimen. We have a little drawing here. So the surface area of the array is the measured width of the array plus an added value for the distance between objects times the measured length of the array plus an added distance for the distance between objects along the length. So it's this rectangular envelope here. That is the surface area of the array, and that we'll get into later how you use that to calculate sound absorption per unit area. One of the benefits of this is if the sound absorption per unit area should remain similar, and well, let me back up one step. The surface area of the array per object will remain the same whether we have 8 objects, 16, 32, 64, and ongoing, because we've accounted for this additional space. So it can be tiled. It has the benefit of, in acoustical modeling applications, one could take the sound absorption per unit area for this array and apply it to a single face, as long as the spacing remains consistent across that face. And it creates, yeah, like I said, like the area per object will remain the same as you use a larger set of objects. There's a second type of configuration that we've started with, which is a single row of equal sized objects with equal space between each. This, think of this, what we had in mind for this, it probably could be applied in other cases, but we had in mind for this are like long linear baffles, let's say vertical baffles that are 96 inches long and tested in a single row of those objects. Similarly, we have the measured width of the array is here, and then we've add the distance between objects to the width. For the length, we take the measured length, and here's the dilemma, and this is something we discussed and debated at an E33 committee for years. This is maybe the one part of this whole thing. We had to pick an arbitrary value because there's no kind of defined value for this additional space. So we settled on 0.3 meters. So for the Americans, that's about 12 inches. That is added to this length. And this does, it's not entirely arbitrary because in the standard mounting type in ASTM E795, that's the space that's defined in the default type J mounting. Also, it's a common configuration to have 48-inch baffles, so it gives you no advantage really to test 48 versus 96 because you'd be adding the same area basically. So the length has this added value of this standard added term of 0.3 meters to get the surface area of the array for a single row of objects. So to calculate the sound absorption per unit area for a set of baffles, we take that A2 minus A1, that total absorption, and we divide it by the surface area of the array. So which was calculated according to one of those previously defined methods. And this gives sound absorption per unit area for the array, or the alpha array. This would be done at 1/3 octave bands. So this would give you your, dare I say, I shouldn't use the term, but I will, sound absorption coefficients for this purpose. You could use it to put into acoustical models. From these values, we can calculate single number ratings. So in section X 2.5, the single number ratings defined in section 3 can be applied to these alpha array values. So for example, the Array-NRC would be the average of the coefficients, or the sound absorption per unit area for 250, 500, 1K, and 2K, rounded to the nearest 0.05, and that would be Array-NRC. When you do this, you have to use a hyphenation prior to the term of the array. So Array-SAA and Array-NRC. There are other reporting requirements. So we're requiring, ASTM is requiring that the area used in that calculation has to be reported alongside. So you would have an Array-NRC of 0.95 over 9.91 meters squared of extended continuous surface area in our example. There are other little things too, like just defining requirements for reporting, spacing, and object sizes and things, just fleshing that out a little bit better than it had been defined in the past. We also have this required statement that just informs people that these values of sound absorption per meter squared and the single number ratings are highly dependent on the exact sample shape, size, spacing, and the extended continuous surface area present in the test and calculations. And that changes to any of these parameters will change the resulting values. These presented results are valid only for the specific configuration present in this test. So that's the subject of that statement is not new. It's not something that is created by this appendix. It does shed light on it, but for object absorbers, suspended object absorbers, the sample size, shape, and spacing affected their stated performance even when it was defined in Sabins per object. So, and other categories of materials, the flat surface treatment materials, they have this issue with other properties as well. So their facing condition or the thickness of the core greatly affect their performance as well. So this is how we are presenting in our formal test reports, how we're presenting these values. So you see we still report the total absorption in square meters and Sabins, and the absorption per object in square meters and Sabins, as we always have. But we're adding this new sound absorption per unit area for the array, the alpha array. Now this is both the Sabins per square foot and the surface area per meter, or sound absorption per meter squared. This value here, so this is like your sound absorption coefficients for the array, and then the single number ratings here. What about past tests? So we've tested hundreds and hundreds of maybe thousands of baffle configurations over the past several years. And there was this period where we knew we needed to do something as an industry, but it hadn't been defined yet by ASTM on what that should be. So Riverbank Acoustical Laboratories was publishing, in addition to, or be outside of the formal test report, we published additional calculation sheets that would answer this question of what is the sound absorption per unit area. And since that hadn't been defined, we did it in all possible ways that we could think of. And so that gave these worksheets here. And as you can see, like we had the method 1 and method 3. Most of the time, the Array-NRC is going to match the method 1 sound absorption coefficient from the total coverage area, but not always. There's certain instances, like for example, the single row of baffles, where our calculation method did not match what ASTM eventually agreed upon. So for rectangular arrays, our method 1 should almost always match. For single rows of baffles, it won't exactly match the method 1 calculation. Yeah, because we did not have that added 0.3 meters to the length. So for configurations that meet, for previous tests of configurations that meet the requirements of this new standard, we will offer revisions to update the past reports to the current standard. There's going to be a small administrative fee for this. I will tell you, it's basically us doing it at cost. And yeah, we're happy to update those old reports to put them in compliance with the new Array-NRC. Now, you're not required to do this, especially if you're reporting values in terms of Sabins per object. Then you have no reason or need to update your past tests. If you want to use the new Array-NRC term, then we believe you should have us update those test reports. Now, someone had asked, could a manufacturer calculate their own Array-NRC values from past tests? Well, the answer to that is yes. Most of the reports will have everything you need, all the information necessary to calculate Array-NRC. However, if you want a formal accredited document with that calculated by an accredited agency, then you'll have to have the updated report. So, all right, and with that, do we have any questions?
We do. So we have the new methods do not take edge effects into account, correct?
Good question. The edge effects, what we call edge effects, are influencing the measured sound absorption, and ASTM C423 does not correct for that in any way currently. There are people working on possible ways to correct for that. This is commonly understood as the reason why sound absorption coefficients in architecture can exceed 1.0, because there's an excess absorption around the perimeter of the sample, which we call edge effects. And there are people, I know Ron Soro and Bob Hallman have been making a lot of progress at ASTM on trying to quantify that so that it could be corrected for in future standards. It's not currently corrected for in this standard. The things that we call edge effects, or those phenomena we call edge effects, are probably more influential on suspended spaced objects than they are even on flat materials. So, because there are more edges.
All right, does Array-NRC correlate to traditional NRC for panels? In other words, would a customer expect the same performance?
Yeah, so in a second here, let me pull up a photo here. Okay, so that's a good question. And that, it gets to the core of why we needed to do something at ASTM and why we arrived at the conclusion that we did regarding how Array-NRC should be calculated. So this photo on the left here gives a good example. So an architect or interior designer might be considering alternate types and categories of material for treatment of this space. So it was very important that the Array-NRC be calculated in a way that provides a fair comparison, because we know it will be used that way. We know that whatever classification we give to this suspended object array will be used to compare to, let's say, a continuous acoustical ceiling tile installation. And so that was the intent with it, that it is a more fair comparison, because let's go back to if you were to try to calculate sound absorption coefficients from, let's say, one face on the baffle, you get an exaggerated coefficient value because the area value you're using, so the sound absorption per unit area, that area value is frankly too small. It's smaller than the area that sound sees. So that gives these inflated NRC values. Like our old reports had apparent method 3, apparent NRC based on one face. So this is basically an unfair comparison. Whereas the method 1, which in this example exactly matches Array-NRC, the Array-NRC is 0.95, which is a fair comparison from a set of space objects to a continuous ceiling treatment. So yeah, that's the intent. It's intended for NRC in general. It's not really an engineering term. It's just a term that's intended for products to be compared. Acoustical consultants would use the sound absorption coefficients or the Sabins per object to specify baffles and treatments.
All right, we have another question. What would you recommend for baffle arrays which are butted end-to-end in the field as installed? I think section X2.3.2, but without the 0.3 separation.
Yeah, that's a good question. So already, since this is published, we've had some new configurations kind of come up. You know, like for example, or like a single object, right, where there is no spacing, but it's suspended in the field. I had in mind theater seats are another thing that this could be applied to. And you know, you're mentioning now baffles where there's no space between. So these are all configurations that can and should be added to later versions of the standard. As a lab, I think we would take it on a case-by-case basis on how we would approach those sorts of things. One of the challenges with this, I don't know if you would call it revolution, but this influx of new products, they're all super creative, and what they're coming up with in terms of the shapes and sizes of material. So it's going to be interesting to see how we add these over time, you know, how many of these new configurations get added. So right now, I don't have an answer for you on how we would approach, yeah, all the baffles being connected together. But yeah, it's something we would take on a case-by-case basis.
All right. Another one, have there been any unique findings of higher than expected low frequency absorption when testing certain configurations of spaced baffle arrangements?
Yeah, that's a good question. I can't think of anything off the top of my head. A lot of the performance that you're seeing and most of the types of products it's just based on the porous or fibrous absorption principle from maybe the felt or the fiberglass in the core. And so the low frequency performance is often limited by the configurations of felt. I do know it seems to be difficult to make predictions on that, and there's maybe an opportunity for anyone that is, you know, wants to figure out how to create computer models to predict performance for some of these structures. It's a challenge because the interactions of sound to these objects is very complex. There might be some cases where they have parts that act as resonators, which is I think what the question is getting at. where you might see like a certain frequency that is seeing a Helmholtz effect and maybe high absorption at that frequency. But most of the time it seems to be a function of the felt. So.
All right, another one is the face area used in the method 3 calculation, the floor plan area. For example, the 2 inches by 8 foot.
Yeah. So, you're okay. I'm sorry. So this is the old way that Riverbank was doing things prior to ASTM C423-23. But if I understand the question correctly, what you're asking, what was the value that was used in this method 3? And in this example here, let's say these are 2 foot by 4 foot baffles and there's 8 of them. In method 3, that area value would be 2 feet by 4 feet. So basically the area of one face times 8. So in this case, that would be 64 square feet. The justification for this, or like the logic behind it was, well, if you laid them on the floor, you'd have 64 square feet of material. But they're not laid on the floor, and they have more than 64 square feet exposed to the sound field on one hand, but they also are attributed to an area of ceiling that's based on the floor plan area. So the Array-NRC in this example is calculated based on the floor plan area, or think of it like the area of ceiling that is attributed to this baffle array.
All right. Do you foresee any type of standardization in mounting methods for baffles for testing purposes, similar to what we have for suspended tiles and panels?
Yes, in fact, thank you for asking that question. So there actually is. ASTM E795, so that same document that standardizes mounting types for wall panels and ceiling tiles, also has a standard mounting for acoustical baffles. We call it type J mounting. The thing is, what you're looking at in this example here is actually the standard mounting. It's a 8 2 foot by 4 foot baffles with 12 inches between baffles in a row and rows 30 inches on center. So what you might be thinking is, well, that's not what our baffles are or how they're installed. So type J can be modified to account for any size, shape, spacing of baffles. So we can modify J to meet what the actual objects are that are being sold. So some product manufacturers that are, like let's say gymnasium baffles, for example, they tend to stick to this 2 foot by 4 foot baffle and do a standard type J vertical. There's also a new J horizontal configuration as well, which has baffles mounted horizontally. So those standard mountings are available, but it can be applied to any size and shape. The challenge is that the results are those changes to size and shape greatly influence the results. And if this configuration does not match your product, it might be pointless to test it at that size, so depending on the situation. I'm always happy to help people figure this out, or kind of conceive of a strategy that works for them and their products.
All right. How long will it take to get this kind of data available on the market to be able to compare more than a few products for people that would want to specify arrays or to calculate the cost-benefit ratio?
Cool. So as of now, as of, what date was that? Sorry, May 10th, 2023, all of our reports that are for suspended object arrays will have the Array-NRC classification, in addition to that savings per object that was always there. So going forward, these will be finding their way into the marketplace. We're also offering all of our customers at a frankly, a very low cost to update their past tests. And so you should start seeing those coming into the marketplace. I will tell you, there is a incredible desire among the product manufacturers to have this. And I think you're going to start seeing it published quite frequently by even some of the very large players. So.
All right. What are some common misconceptions or mistakes you notice when acoustics are evaluated for projects?
Well, I mean, generally there's a lot. That's probably a whole webinar. But let me think in terms of this presentation. Yeah, I would say kind of the one thing I've been going over this, just to think of sound absorption coefficients. Start thinking of sound absorption coefficients and NRC as absorption per unit area. Now we have these metaphors, like I said, we think of them like the absorption coefficient as the percentage of sound absorbed, and that made sense for flat panels. But as we started to get into three-dimensional structures, NRC was being requested, but it made no sense because the area value wasn't defined. Now ASTM has actually tried to define an area value for these, but I would say that falls under the a common misconception, maybe that that NRC is like the percentage of sound absorbed, although that's close. It's not actually the definition.
How should we handle vertical floor standing baffles? The footprint for vertically oriented baffles would be much smaller than if the same array was suspended horizontally.
Okay. So there's a couple things in there. So one, the floor standing baffles, let me get back to my picture. So the type J mounting, this suspended spaced object array mounting method, it assumes that there is a sufficient distance from the objects to the test surface to where the reflected sound off the test surface is no longer influencing the absorption. So meaning you won't see different results if this set of objects were spaced 12 inches higher or 24 inches higher. They're in the diffuse field of the chamber. But as the set of objects, if they were lowered close to the test surface, that reflection off the test surface would start to influence their absorption. And then that would become one more critical parameter that of the test, where you would have a distance, of 0 or 10 millimeters or 25 millimeters, where the objects are from the test surface, and those results are only relevant for that specific distance. So it is possible for us to test space object arrays that are contacting the test surface or are close to the test surface, but we have to designate them specially for that condition. So yeah, it is possible to test close to that, and Array-NRC would be, I'm going to say that I think, based on my understanding of the text, that Array-NRC would be applicable to that as long as that was properly reported. So Array-NRC could be applied there.
Right.
Now, horizontal versus vertical, I think might have been in there too. Array-NRC can be applied to horizontal clouds as well. So really what the examples are showing vertical, but these same definitions would apply even if the object was suspended horizontally, because you would have equal size objects with equal space between each object in a row and equal space between rows. So regardless of what the shape or orientation of this layout calculation would remain the same.
All right, can you apply this to a series of floating clouds, or does it only work for long slender baffle style?
Yeah, great question. Thank you for asking. So the good news is first, right now we've defined S-array for two different configurations. So ASTM E33 committee, these are the most obvious and most widely used configurations. However, there will be more added over time. Like for example, I think one I would like to take on possibly next would be theater seats. So if there's not a current definition, that doesn't mean that it'll never exist. In fact, we'd welcome you to come participate in the E33 committee and help with us to create a definition for it. There's some types of configurations which might seem straightforward, but when you start thinking about the geometry, defining them gets tricky. So for example, triangular arrays. We'd like to try to define this for that as well, but actually that we'll talk about that later, but that gets more complicated than you might think. So anyway, right now we have it defined for sets of objects in a rectangular array, meaning equal spacing between rows and equal spacing between objects in a row. So that could be vertical or horizontal. It doesn't have to be vertically suspended array objects. They could be horizontal objects, as long as that spacing is rectangular. As long as the configuration of objects is essentially rectangular.
Okay. We have another one. How do you see acoustical consultants using the data in calculations? What would be the preferred method?
Sounds good. So acoustical consultants will have a new tool in their toolbox. So hopefully they will still have access to the Sabins per object calculation, which they will use the way they always have in using the Sabin equation to predict reverb time, and then entering that based on per object versus per square foot. However, in acoustical modeling software, they often don't accept the Sabins per object parameter. So they will have this coefficient for the array, or the Sabins per square foot for the array, which could be assigned to a face in an acoustical modeling program. If the spacing remains consistent with what was tested, then those coefficients that come out of this new version could be applied to a single face that is entered into an acoustical model. That was one of the side goals of this. However, ASTM E33, we don't officially endorse the use of the results for that purpose, but we know that they're commonly used for that purpose, and we think about that when we create standard mountings and when we do these calculations. So yeah, you have a new tool in the toolbox, and this could be used in acoustical modeling programs. But watch out for that object spacing.
All right. Another one, is the NRC method 1 from the last table the same as E84 for wall and ceiling panels?
Well, I think E84 is that a fire flame spread test? So I'm not. Could you follow up in the chat box? Could you follow up on that question? Add a next question. By chance, were asking about something different? So in most cases, the Array-NRC will be the same as the method 1 from the old way in most cases, but not all cases. That's why we're encouraging manufacturers to have these revisions made.
Okay. Going along with that.
Sorry, let me clarify one thing. We're encouraging manufacturers to have the revision made before publishing Array-NRC as a rating. Sorry, go ahead, Becca.
Okay. When do we need to start to revise the existing reports?
Well, you don't. Theoretically, you never need to. Those results will always be relevant, and especially if you are presenting your sound absorption in terms of sound sabins per object, then there's no need to have the revisions made at all. The only time you'll need to make these revisions is if you plan to publish Array-NRC values. If you are publishing Array-NRC values, I recommend that you have the revisions made.
All right.
One of my customers had asked if they can make the calculations themselves, and actually, yes, they can. Most of our reports include enough information where one could make the Array-NRC calculations themselves. However, in order to have an official document from us with the Array-NRC calculated by a NAVLAP accredited agency, we would have to do that. And like I said, we're not treating this as a profit maker. We're basically doing this at cost to get everyone up to speed. So.
All right. Will there be a standard size and configuration of baffles when testing? Example, baffles must be 12 by 48 inches. Spacing must be X between units.
Yep, good question. So it currently exists a standard mounting for baffles. ASTM E795 is the mounting standard. And many of you that worked with me in the past, I'm usually helping you to figure out, is it type A mounting, is it type D, etc. And you may have heard me say a type J, or this is a type J. Well, type J actually has a specific configuration as the default, and this is 8 baffles that are each 24 inches by 48 inches and spaced 4 rows of 2 with 12 inches between objects in a row and rows 30 inches on center. So that is defined in E795 as the standard default type J. However, it says that any other type of baffle or configuration can be tested. It just needs to be documented on what it is. The nature of these products is that they're very highly designed typically, and they're very creative in terms of their shapes and sizes of baffles, which creates a challenge for that standard. So because they're not that standard shape and size. So let's say you're making the traditional like gymnasium baffles, let's say. Those I'd recommend you do at that standard default type J 24 by 48 configuration. Let's say you're making acoustic light fixtures or CNC shaped, CNC cut felt baffles that are highly creative. Well, unfortunately, that standard configuration, it doesn't work for you, and you pretty much are forced to test at your actual size and shapes. I know that's a dilemma because some of them have hundreds of sizes and shapes. That's a struggle that everyone in that industry is working through, and they're trying to figure out, optimum ways to address that. I would say contact me offline, and I'm happy to help work with you on, what's the best place to start for such a thing.
All right. With the array calculation, we can determine the overall surface area covered by the sound absorption array. However, I'm curious about the vertical surface area that each suspended sound absorption object presents. Could you provide any insights on this?
Yeah, so let's say we're talking about vertical suspended baffles. ASTM has created this new rating and classification based on that area, that horizontal area in that instance, or think of it as the area of ceiling treated by the array of baffles. But I know in the past, you know, some people have calculated it based on that vertical face, and that gave a perceived benefit, and that because the area, especially if it was only used from one face, that area was very low relative to the sound absorption measured. So it gave, you know, crazy high apparent NRC ratings, like 1.6 in this example. I honestly don't know how we've been working with these categories of products more and more over the last decade, and I find this approach to not really be helpful to anyone. It's not most fundamentally, it's not a good comparison from baffles to other objects, or even from one baffle to the other. So whereas this method one provides a more even playing field, or a better basis of comparison for arrays of baffles versus continuous treatments, like spray applied cellulose, or acoustical ceiling tile, or all these other things. Like, you have a fair basis of comparison. But with this method 3, there's this calculation, which is, it's not the same thing. It's not really a fair basis of comparison. So that said, you could still do these calculations on your own, because every report will give the total Sabins, and you could make calculations like this for your own engineering purposes. This method 2 approach might be, this is the absorption per square foot calculated from the total exposed surface area. I think this might be useful. More work needs to be done, but this might be useful for engineering purposes. I'm like trying to predict what the Sabins per object might be on different size objects. This might be helpful in that way, but honestly, I don't know of anywhere where this method 3 actually is helpful, other than that gives a very high number.
All right, we got a follow up to the one question from a little bit ago. They said, ignore the E84 part. Does the NRC method 1 from the last table correspond to NRC numbers for wall and ceiling panels?
Oh, yeah, okay, I get it. Yes, method 1 is the most comparable to continuous treatments. And that's why I pushed for Array-NRC to basically be in that format of method 1, because it's a fair basis of comparison. Let's say I have a acoustical ceiling tile installation in my office, and I want to replace it with something equivalent to that, but I want it to be suspended baffle array. Method 1 gives you the equivalent NRC for the ceiling installation, and therefore Array-NRC, because it's essentially the very similar calculation, exactly the same in most cases. It gives that sound absorption per square foot area of treated surface, which is exactly how sound absorption coefficients and NRC are calculated for acoustic ceiling tiles and wall panels.
All right, another one. This is good, lots of questions. All right, is there consideration in this new testing to account for products or baffles with differing depths of system? For example, what about a series of baffles where some are 5 inches tall, some are 10 inches tall, and others are 20 inches tall?
Yeah, very good question. So let me see. So it's that parameter is similar to what thickness was in acoustical wall panels. So you'll have different NRC ratings for different thicknesses of acoustical wall panels. You will also have a different Array-NRC for different depths of baffle. So because you'll have more fuzz per square foot of ceiling for a deeper baffle. And this will turn into one of the trade-offs for designers. Sometimes the designers want thin profile baffles because they don't want to lose their ceiling height, right? But you'll get a higher Array-NRC if you use a deeper baffle. So that'll be a trade-off and consideration for acoustical designers. This new classification does not create that problem. That problem always existed because in the previous sabins per object, you would also have different sabins per object for deeper baffles because one object will have more area of fuzz.
Another one, what if the rectangular array overlaps? For instance, if the baffles are at an angle, something like a window blind.
That's currently not defined, but join ASTM E33 committee and you can work out a calculation for that. So we could be added, you could be an X 2.3.3 for overlapping arrays. That's a rare configuration, but I've seen it. I know exactly what you're talking about. Yeah, it's currently not defined, but it's something we could add. It's something ASTM could add to the standard.
Okay. Is there a difference in performance when an array is suspended close to the structure versus further away from the structure?
Yeah. So in the mounting method, and I can't off the top of my head remember the exact distance, but greater than a certain distance, then we consider that the distance is no longer critical. It's in the diffuse field of the room. So that's why most of the type J mounting don't give like a airspace designation. Like let's say like type D, which would be on wood furring strips, you'd have a D50 for 50 millimeter wood furring strips. But type J's are in the past had always been just type J because the structure is basically suspended far enough away from any walls or test the floor of the chamber where that reflection is not as critical. However, it is possible to test object arrays at a closer distance to the test surface, and then that distance becomes part of the designation. So then these would be objects tested at a 1-inch distance. So it's as critical as like a D50 versus a D25, how that 25 millimeters is considered to basically invalidate the test if it's not mounted in the field at 50 millimeters or 25 millimeters. It would do the same thing to type J. So most of the time we're testing these space object arrays far enough from the test surface where that gap is considered to be, or that airspace depth is considered to be so large it doesn't influence the performance. But it's a consideration in the field. The good news is testing it or installing it in the field closer to the ceiling typically has a favorable impact. So from that standpoint, it shouldn't be worse than the lab configuration.
All right. This one, thanks for advocating for a Sing Array-NRC. What would it take for the architecture community to adopt the SAA standard?
Very good question. This is something that we argue about at ASTM all the time. It's sort of a running joke that we, as a committee, that we could get too far ahead of the architectural community, and the architectural community could just completely ignore what we do at ASTM. So it's a persistent warning. There is actually, I think that there is an answer to this. For a long time, I've believed that it was like the product manufacturers. So if the big major ceiling tile manufacturers all at the same time decided that they were only going to publish SAA, then maybe that would force the change. But after speaking with some people, maybe they feel as kind of at the mercy as the industry as everyone else. And I think what my current understanding is, if it was written into specifications, if SAA was a requirement that was written into building specifications, then the product manufacturers would get in line and start advertising SAA. So I think that's where it has to happen. So it has to happen like on building codes or performance specifications. So something similar happened on the transmission loss side of things. Recently, the International Building Code was updated where it defined the field test standard to be NNIC, and then suddenly everyone's asking for NNIC. So I think it's something similar to that. Once it's in those specifications, the manufacturers will fall in line.
Yeah, and like we said, if you do have any other questions, feel free to reach out to Eric directly at info@riverbankacoustics.com, or the phone number is on there as well.
And feel free to reach out at any time, even if you have questions. I'm always happy to talk about these things. And just I'll also make a pump for the ASTM E33 committee, where we develop these standards. That organization is open to new members from all levels of acoustic expertise. Thank you all for your time, and look forward to seeing you next time.